Okay, that's perfect. So just one word to introduce the today's speakers. Rachel Adam will start first, and she's recently graduated as a master's student from Arizona State University. She has worked with Dr. Scott and Harrowsmith to create a systematic mapping process to map tectonic faults and document supporting geomorphology in order to try to predict future surface rupture locations. And then let me, admit people. And then Dr. Chelsea Scott will take the floor and give a presentation. And she's also from Arizona State University, where she's an assistant research professor. She got her PhD from Cornell University, and in her research, she combines remote sensing techniques with geomorphology and structural geology in order to study mainly fault displacement hazard, fault slip rates, and fault structures. And she's also among the leadership team for open topography, which I think we all know and use a lot this site where they have very, very cool data and processing tools. So, okay, well, I give the floor to Rachel, so you can start, and we will have some minutes for questions at the end of both the talks.
Great, thank you. And I think Chelsea is just going to do the first couple slides, and then I'll take over.
Yeah, so good afternoon, good evening, good morning. Thank you everyone for coming to our presentation. Rachel and I are very happy to present some of the work that we've been working on, specifically with PG&E over the past few years. And I'd like to acknowledge the many collaborators that we have on this project, and you can see all of their names printed here. So our talk is evaluating a systematized active fault mapping approach used to predict earthquake surface rupture locations. And then on the next slide, by way of introduction, we have a few points here. So accurately locating tectonic faults is challenging because geomorphic evidence for faulting can be obscured by surface processes. And we found that even experienced fault mappers can interpret the same landscape differently. We are developing a systematic desktop-based fault mapping approach using remote sensing data such as topography and imagery to map tectonic faults. And we envision that this approach will improve the repeatability and accuracy of mapped fault locations. In this project, we've had students and consultant mappers create fault maps from imagery and topography acquired before several historic earthquakes. So today our presentation will be in two parts, each about 20 minutes. And the first part will be given by Rachel, and she will be discussing this fault mapping approach, as well as some listening sessions that she's conducted aimed at understanding how individuals approach fault mapping. And then I will give the second part of the presentation that will focus on the uncertainty in the location of mapped faults, and this is a key input into fault displacement hazard analysis. So, Rachel.
Thank you, Chelsea. And then I think we wanted to save questions to the end, but if anything I'm saying is unclear, please feel free to interrupt me and ask. But just a bit of an outline about my presentation. First, I'm going to talk about teaching the fault mapping that we introduced into two courses at ASU and University of Nevada, Reno. Then I'll introduce the fault mapping process or systematic process that we developed to introduce to students and consultants. I'll then talk about the geomorphic indicator ranking system, or the GIR, is the system that we created for the mappers to use and the GIS software to map the geomorphology. And then I'll go into one of the analyses that we did after the fact when we got all the data from the mappers to measure the distance between mapped geomorphology to subsequent coseismic rupture traces. And then I'll talk about the listening sessions as well that I conducted with all the participants to better understand the mapping process. And we did want to give a forenote about what the pre-rupture mapping process is. And so the idea was how well can we anticipate future rupture locations? And so the idea is to fault map remote sensing data sets only acquired before the earthquake of focus to map, could we have anticipated where it would rupture if we don't see where it actually ruptured? It's important to note that we don't use any field work for this. It was a little difficult also to do that between all the different universities that were in the project, and we wanted to see just how well you could do without trying to validate or fortify the fault location in the field. And so a bit of motivation for creating this systematic process. So current fault practices use a range of techniques to try and ascertain an accurate fault location. But the idea for us was to build upon as much evidence as we possibly can before getting to a final fault location. So that includes mapping all of the geomorphology, surficial geology, and morphology to then build and iterate upon evidence to then create a fault confidence ranking. All of the mapping that we created is a consistent symbology, because oftentimes it depends on different maps. They could all use different symbology and they could be mapping the same thing, but interpreting the area differently. We hope that with this kind of systematic, broad symbology, that it's going to improve the overall quality of the fault maps and make it a bit easier to understand, disseminate, and compare to ultimately improve the fault displacement hazard analysis. And so when we talk about teaching the fault mapping, ASU partnered with University of Nevada to teach 2 iterations of the course, and was with Dr. Rich Kohler from University of Nevada. And we also had students from Oxford and McGill as well. The students ranged all the way from undergraduate to postdoc level. And the idea was to emphasize to all of the students, regardless of their prior experience with fault mapping, to build upon evidence first and observations before jumping to conclusions on the fault location. And so on the right side is a figure where we had all of the mapping locations. They used a pretty wide range of magnitudes, the type of climate from semi-arid, arid to subtropical, and different mapping areas and slip senses. The idea for using the students kind of as our test subjects was that we didn't want them to have any prior knowledge of the earthquake, so that our fault mapping process could be tested without people already knowing what the fault looks like and jumping to a conclusion on fault location and mechanics. And this is a little snippet of class in Zoomlandia. So you see Chelsea and Dr. Aerosmith and Rich, the professor from UNR, and Chris Madugo from Pacific Gas and Electric. And so this is the ideal mapping process. This is kind of a step-by-step guide of how we introduced fault mapping to students and consultants. You start with a research question, which is how can we anticipate earthquake hazards by just making a fault map utilizing tectonic geomorphology? We give all of the mappers data before. It could be DEM, optical, or a range of remote sensing. And you'll make certain derivatives with that, hill shade, slope maps to better enhance the interpretation of the landscape. You'll then move on to the preliminary mapping, where you map the morphology, concave, convex, slope breaks, surficial geology, which would be advantageous in like arid landscapes or alluvial fans, or geomorphology, trying to work at a fine scale, working to a large scale. You'll then move on to the GIR mapping, which is our shapefile, where you plot all of the points in a point shapefile for evidence of faulting. You'll then map the fault line without using our confidence ranking yet, just to ascertain the fault location, and then apply our confidence ranking. But I will go through each of these steps using an example from one of the mapping assignments that we introduced to the students. And so this is a example from Washoe City, Nevada. It's in western US. It's a pretty arid landscape, but this is one of the assignments that the students had to create a fault map for. We gave them a DEM, and you can make certain derivatives of it. In this example, I made a hillshade, and you could change the illumination to better enhance the landscape. For this one, I illuminated it to enhance the drainage networks and the range front on the left side of the screen. Then you do your preliminary mapping. There's no hard or fast rule of which preliminary mapping would be most advantageous. Oftentimes, I'll combine a little bit of all of them, like morphology, superficial geology, and geomorphology. And so this example, I like mapping out all of the drainages to see if there's any disturbance in like the natural progression of the drainage network. I'll map out the ridges to see if there's any disturbance there, any shutter pressure ridges, slope breaks, because I don't want to necessarily make the notion that there's scarp yet. So I'll just map out anytime I see a slope break. And it is helpful, at least especially when we are teaching fault mapping to novice mappers, to map out all of the anthropogenic alteration, which can include streets, houses, farming, and so forth, to try and separate anthropogenic lineations from faulting lineations. And I also do like to map the extent of all the landslide and debris flows, which you can see in the green polygons here. But the idea is when you're doing the preliminary mapping, you want to map everywhere with a consistent coverage so you're not missing anything that could be mistaken for faulting. And before we implement the GIR system, I wanted to talk a little bit more about it. It is a tool that we created in QGIS, which is an open source mapping software that we introduced for the students. The idea is that we consolidated most of the tectonic geomorphological features that are indicative of faulting, and they're given a rank from 1 to 4, depending on how indicative of faulting they are. So on the left side here, you can see what that table looks like, at least just for the first few lines, where we have listed a feature in offset drainage channel. It's given a rank of 4 because it is almost unequivocally caused by faulting if it's identified correctly. And then we also include features called modifiers, and those are given a plus or 1, and those are mostly used to fortify or diminish the mapper's confidence of other stronger feature placements. So a linear valley or drainage isn't enough on its own to indicate a fault, but when it's mapped in junction with other stronger features, it can increase the mapper's confidence of the fault location. And below here, you can see an example of this from Wallace Creek in California along the San Andreas Fault, where you've mapped a couple features, the offset terraces, offset drainage channels, quaternary scarps, and then these gray are the modifying features where there's anthropogenic alteration, alignments, and linear valley drainages. We wanted to understand the strengths of this tool, and we wanted to introduce it to the class and to the hired consultants to see from their perspective if there is a strength and how we can improve upon it. So now that I introduced the tool, this is what it would look like when you would use it in a mapping project. It's pretty much based entirely off of the preliminary mapping, but you can see that along this range front, this TF is a triangular facet, and there's some QSP markers here. And each color is according to how like the rank of the feature. Red is a rank of 4, green is orange, and so forth. And I'm going along and mapping every time I see certain features, but I also have things that are diminishing my confidence along this range front, like a landslide negative where it's obscuring the evidence of faulting, or the erosion right there where the quaternary scarps aren't as strong. It's helpful then you're going to map your fault. You're not going to use any of our symbology for that. You're just going to do a simple fault line to just make sure the fault location is exactly where you want it before you apply our ranking scheme. But once you are confident with the fault placement and traces, then you could apply the confidence ranking. And this is another shapefile that we created in QGIS. And on the bottom right, you could see some of the symbology. The mapper uses, hopefully they'll train their eye with GIR, just the quantity and the ranking and clusters of GIR features that can then inform their confidence of how strong they are, not only in the fault's location, but the strength of the fault as well. So they'll distinguish between strong and primary and secondary first, and then there's 4 categories: strong, distinct, weak, and uncertain. So where I had placed a bunch of triangular facets and scarps, I am pretty strong that the fault is along this range front. But then in other areas where I don't have as many GIR placements, or it's more prone to erosion or anthropogenic alteration, I've lowered my confidence for that. We gave all of these tools to the students in the class, and then afterwards we hired 6 consultant mappers to complete the same maps that the students did, to acquire as much data as we could, to then complete some subsequent analyses on them to test the strength of the system as a whole. And so one of the analyses that we completed was the feature to rupture distance analysis. And this is where we are measuring the distance from the GIR feature to the closest co-seismic rupture, like published fault maps after the fact. Those are shown in yellow here. The red is the mapper's fault lines, and the GIR points are here. It's just measuring the distance, the closest distance to the next surface rupture feature. The idea behind this is that we wanted to see which features are stronger indicators of fault location than others. And that's just kind of measuring the distance between them and getting some metrics off of it. So here is an example from a mapping area in El Mayor Cupa. And you can see all of the GIR points right here. There's a lot of ranking features up here in the alluvial fan, and then along the range front as well. In A, most of these features mapped a prior rupture already, the 1892 Laguna Salada rupture. And a lot of the GIR feature placements matched that, and they mostly included quaternary scarps and offset or cut alluvial fan placements. And then along this range front here, there was mostly bedrock scarp placements and triangular facet placements. Unfortunately, the 2010 rupture did not occur along this range front. Although we know there is a fault there, it had been the location of the fault had been fortified with field work prior. So there we know there is a fault there. But with our pre-rupture mapping technique in that specific rupture, it did not go along the range front. And so that kind of represents aleatoric variability, where there could be strong tectonic geomorphology and field evidence for the fault, but it's not going to rupture in every earthquake. But after we completed the analysis and measured the distance from the GIR features to that surface rupture in yellow, these are the top features. We measured the 16th percentile, the 50th, and the 84th. The 16th generally represents some of the closer distances to the surface rupture. The 84th measures generally the furthest distance away. And a couple things to point out is that the quaternary scarp and the offset and cut alluvial fan have a very low 16th percentile, and that represents that they are pretty strong indication of fault location, and they are mostly mapped in that alluvial fan where the rupture actually did occur. However, the bedrock scarp and the triangular facets have a much further and larger 16th percentile meter distance, because they were mostly mapped along that range front where it did not rupture. So it can skew our results a little bit if we can't anticipate exactly where it's going to rupture.
Excuse me, Rachel, may I ask a question? Can you go back to the map?
Yes.
Before? I didn't understand the source of the data from the 1892 Laguna Salada rupture.
The source
what
of
is the reference?
Sorry?
The reference of this map?
It's a published map, and this one was specifically acquired from Alex Sarmiento's fault.
This is on the database.
It's Rockwell. Sorry, I'll jump in if it's from the FDH database. Rockwell and someone. I'll paste the link in the chat.
Okay. This is surprising that the Laguna Salada 2016 earthquake is less not accurate. I don't know if this is the right word, but the trace is less resolved. Let's say, I don't know.
Yeah. Mm-hmm. And this is a very small little snip of the entire rupture too. It's super expansive. So this is just like across that one alluvial fan. But if you were to take all of the line work and the points away, you can see there is pretty clear evidence that was because it's so arid that it still remains from the 1892 rupture. And that's why a lot of the mappers tended to put the GIR placements there and not where the 2010 rupture occurred.
Okay, thank you.
Mm-hmm. Yeah. We performed this analysis for all of our mapping areas, and this is a summary plot of that showing the quantity, the 16th, the 50th, and the 84th. A couple notes for this is that the cut or offset alluvial fans performed the best. These were mostly mapped in that EMC location, and it's likely because they are well preserved in an arid landscape. The next best were quaternary scarps, and they had an average feature to rupture distance of 5 meters. They are normally well preserved and in fresh locations. The bedrock scarp in the middle here has a further distance. Not only might have been skewed from that EMC location, but also there is challenges in locating bedrock scarps that are eroded or not ruptured recently. Two features of note that performed better than we originally thought were landslides and lineations in topography. Landslide performed the third best and lineation performed the fourth. And these are originally just modifying features +1, but with their very low 16th percentile feature to rupture distance of 5 to 6 meters, it does go to show that sometimes it can serve as a positive modifier, a strong indication of faulting if it's mapped correctly. And finally, I did want to talk about the listening session. As we were teaching the class, we wanted to try to incorporate some geoscience education research, and we wanted to better understand the fault mapping process, how certain people with varying levels of experience or the same level of experience can differ in their fault mapping process, and also wanted to get a better perspective of what our process that we introduced to the class looked like for them. To do that, we conducted 30-minute listening sessions with the professional geologists and 12 students in the class. We modeled this methodology after a guide from Oregon Health and Science University, and we conducted the sessions over Zoom while the participants shared their screen open to the QGIS mapping software. So we recorded and transcribed the sessions, and we received approval from ASU for a study with human participants. And the idea was that they would open up their mapping software to me, whatever project they were working on at that time, and I would ask them certain qualifying questions about their mapping process to get a better sense of what they think of mapping. And we would record and transcribe them using an in vivo software. This is what it would look like. This says a student opened up to their Washoe City mapping assignment, and I would take them around, ask them general questions about their mapping process and maybe more specific questions about certain mapping decisions that they made for that time. After each of the sessions, I would transcribe them, and this is a screen cap of what the in vivo software looks like. It's a qualitative coding software, and each of these blocks of text indicates a different participant's response. You can tag and kind of code, quote unquote, different phrases or terms or sentences that the mappers are saying and the participants are mentioning. And on the right side, you can see some of the things that I'm coding, something about their mapping process. Someone mentioned geomorphic mapping. Someone mentioned a generalized term of what their process looks like. I like to look at patterns far away, close together. And I would do this for every single interview, every single listening session, and code all of them to get certain metrics and themes out of it after the fact. And so this is kind of an example of what that would look like. I would ask the participants what features immediately pop out to you. What do you look for first when you create a fault map? And so a consultant mapper that had a bit more experience said most often the faults are responsible for breaks and slopes, scarps, aligned ridges, troughs that are persistent across an area and are somewhat laterally extensive. And there was a senior student mapper who described it as seeing a linearness and it's connected like across the range front. And so they are using different terminology. And this was a common theme that we would find across the board with people that had a lot more experience, were more confident using more high-level terminology, where senior or like novice mappers would use more vague terms to describe what they were seeing. And some other things that we noted is that a lot of times people are looking for linear indication of faulting, lineations, scarps, disruption in the natural progression of the landscape. And out of all the features that they were mentioned, 79% of them were linear when I would ask them what they look for. This also correlated that the linear features did perform well in the feature to rupture distance analysis. So it does go to show that looking for lineations and linear features is a good first step in trying to identify faults, but it shouldn't be relied on wholeheartedly, as if it's misidentified, then it can lead to an incorrect fault location. And then just some conclusions from my part of the presentation is that we developed a systemized and well-documented approach to make potentially active faults and the supporting geomorphic evidence using only desktop and remote sense-based approach. We want to emphasize with this approach that we're documenting all of the evidence before making any conclusions about the fault location. And we made this using a well-defined GIS-based tool to map geomorphic evidence and also rank the confidence of the resulting traces. We believe that our geomorphic indicator ranking system is an effective tool to systematically doc geomorphological evidence for faulting in a systematic and repeatable manner. And then based on all of the resulting fault maps, we found linear features like scarps, lineaments, topographic lineaments. They performed well as good indications for future rupture location. And the listening sessions we conducted with the participants show that mappers are preferential towards linear features, and they identify faults, and the experience level of each participant impacts the language that they use to describe their evidence and thought process. And so we are finishing up a paper based on this part of the research, and we're planning on submitting it early next year. So keep an eye out for it, but I'll switch it over to Chelsea.
Thank you, Rachel. Can you share? Everyone can see my screen?
Yes.
Okay, thank you. So for the rest of this presentation, I will discuss our work on fault location uncertainty. And our goal from this part of the project is to evaluate the uncertainty in fault location using this desktop-based approach of regional scale mapping of remote sensing data sets. And we actually did this part of the work before we developed that systematic fault mapping approach that Rachel discussed. And actually this work served as partially motivation for that. And so the maps that I'll show you here are mapped with a little bit less of a mature mapping system. We had three major motivations for this project. First, we were interested in looking at fault mapping with remote sensing data. And we wanted to simulate pre-rupture fault mapping. And so we essentially had to use this remote sensing data to understand what the landscape looked like before these historical earthquakes occurred, so we could really simulate true pre-rupture mapping without knowledge of the subsequent earthquake. We also wanted to learn more about using this remote sensing data, as desktop-based mapping is becoming more common as fieldwork is logistically challenging and expensive. A study had been done about a decade earlier by Peterson and colleagues looking at fault location uncertainty in arid landscape of Southern California along largely strike-slip faults. And so we were interested also in understanding the uncertainty in fault location for broader type of faults in different climates. And finally, we were interested in understanding how well we can teach students to map faults in a semester-length course. So in this study, we focused on 7 historical earthquakes with strike slip and normal sends of motion They occurred in a range of climates with magnitude ranging from 6 to 7.8. And in today's presentation, I will focus on this Bora Peak earthquake here in Idaho and the Kumamoto earthquake in southwestern Japan. Today, for the outline, I will discuss the pre-rupture mapping, the rupture prediction analysis, uncertainty statistics, and an application. So this work has been published. It was published earlier this year as an open access publication in the journal Geosphere. I would like to acknowledge the 25 or so co-authors on this paper whose experience in academia, industry, and geologic surveys really added a lot of perspectives to this work. You can see all of the co-authors there. So I'll discuss several of the pre-rupture map results from our study. This is looking at the 1983 magnitude 6.9 Bora Peak earthquake, which again occurred in Idaho. So one of the major challenges of this project was locating high quality imagery and topography acquired before the earthquake. This example here shows a topographic hillshade generated from 1950s aerial photography that was collected by the United States Geologic Survey. And in the fault mapping, we asked the students and the professionals to label the faults as primary or secondary, and then with a confidence ranking from strong, distinct, weak, or uncertain. We gave the students some guidance for these criteria, but also asked them to accommodate to make them best for that local area. So this is looking at the left for the map for the Bora Peak earthquake, and this map was completed by a senior PhD student. And the student mapped largely primary faults here along the range front, mapped some secondary faults along the foothills, and then this transbasin uncertain fault here. Here is an example of another one of the pre-rupture fault maps. This is for the 2016 magnitude 7 earthquake in Kumamoto, Japan. And in this case, the LiDAR data was acquired, in fact, just hours before the earthquake following a significant foreshock. And this area was very challenging to map, as many of the fault signals looked very similar to the geomorphology that could be generated from fluvial activity. So here's the fault map, and you can see here it's beginning to the west where the earthquake initiated. The mapper put these three approximately subparallel faults that collectively bound the range front, are concealed under young alluvium, and offset and abandoned terrace. And then to the northeast, the faults are indicated by this range front that becomes increasingly steep and linear as we go towards the northeast. So the next question that we looked at was, did these mapped pre-rupture faults predict the location of the subsequent coseismic ruptures? We answered this question in several steps. First, we assessed which coseismic ruptures were predicted by the pre-rupture mapping. We then determined why the missed ruptures were not mapped. And we finally calculated statistics about the coseismic rupture prediction and the rupture to fault separation distance. And I'll discuss each of these in the next slides. So first, we looked at how the mapped pre-rupture faults predicted the location of the subsequent ruptures. And in particular, we had two criteria, and the first one is shown here. And this is that the rupture to fault separation distance is less than fault confidence-based distance thresholds. And so those thresholds are shown there. And so to pass this criteria, for example, a strong or a rupture had to be within 50 feet or 50 meters of a strong fault. And these distance thresholds were partially inspired by the fault location uncertainties in Peterson et al. 2011. And this example on the right shows a predicted rupture, where here we have a fault in red and a rupture in orange that are essentially overlapping across an offset terrace. And in this case, the fact that there are overlapping indicates that the rupture and fault pair do pass this first criteria. Second criteria is a little bit more complicated, and it's that the rupture and nearby mapped fault have to interact with the landscape and the geomorphology in the same way. And our first motivation for developing this criteria is that we wanted a rupture and fault that were essentially conjugate to not be associated with a predicted rupture. And so here in the top right, you can see an example. Again, this is the predicted rupture example that I showed on the last page, where the rupture shown in yellow or in orange and the rupture or the fault in red, that pair is associated with a predicted rupture. And on the right, you can see an unpredicted rupture. We have still the fault in red and the unpredicted rupture in yellow. And in this case, the fault is at the base of the hill slope and the rupture is a little bit upslope. And because the fault was mapped as strong and these two linear features interact with the landscape in a different way, being at the base and upslope, we determined that this case, the rupture was unpredicted. And the criteria for interacting with the landscape in the same way do get looser for decreasing confidence in the mapped pre-rupture faults. And we also determined why unpredicted ruptures were not mapped. And so those reasons are shown here, which I will discuss briefly. So a rupture could be unpredicted because the mapper did mapping at low resolution. And in this case, they're not using the full resolution of the pre-rupture data, whatever resolution that data is at. Second is that the rupture could have been missed because there was low quality data. So in this case, maybe there's a hole or an error in the topography data. It could be a wrong geomorphic interpretation. For example, the rupture and fault could be at opposite sides of a sag pond. The pre-rupture mapper could have missed what I would determine to have been fairly obvious pre-rupture geomorphology. And in this case, the mapper likely just didn't look at that particular area and missed something fairly prominent. The landscape could have a short preservation potential. For example, we may not expect ruptures to be well preserved in a swamp. Ruptures from a previous earthquake to be well preserved in a swamp. And finally, last case is that there was no unambiguous fault in the pre-rupture topography. So I'll now go through and discuss this analysis for two of the earthquakes. So here we're again looking at the 1983 Bora Peak earthquake. Here's the pre-rupture map I showed before, and this map shows the ruptures. And in this case, they're colored orange if they were predicted by the pre-rupture mapping. And this case largely occurs to the ruptures that were located along the range fronts. Many of the missed ruptures are missed because there was no unambiguous fault in the pre-rupture geomorphology. That includes here in the foothills, where there really was minimal at best signal of a fault in advance of the earthquake. And then There's also very limited signal of the faults here across this transbasin fault. And in fact, paleoseismic work has shown that this transbasin fault doesn't rupture every time there's a large earthquake along the range front. And so its geomorphic evidence of faulting there is lower. And here's that example analysis looking at the Kumamoto earthquake. In this case, we find in orange that many of the ruptures that occurred along the range front were predicted by the pre-rupture mapping. Those again are shown in orange, and in blue, these were the missed ruptures, and they largely occur in these agricultural landscapes with limited to no preservation potential. So I will now discuss the rupture prediction analysis. And our two questions were what percentage of rupture locations were predicted, and what is the separation distance between the mapped pre-rupture faults and the ruptures. So to do this analysis, we first resampled the fault and rupture line work to a 1 meter vertex separation, which essentially gave each meter length of the rupture and fault the same weight in our analysis. And then we calculated the separation distance as that second norm distance or separation between each rupture vertex and the closest mapped pre-rupture fault. And so on the right, you see an example of this analysis for the Napa earthquake, where the black shows the mapped pre-rupture faults, and the blue to yellow shows the coseismic ruptures that are colored by the distance between that rupture and the closest pre-rupture fault. So I'll now go over the statistics from our work. This table is showing the percentage of ruptures that were predicted for the full set of pre-rupture maps that we completed. And this shows that the pre-rupture mapping predicted 10 to 51% of all ruptures and 12 to 68% of the principal ruptures. Based on these numbers, we conclude that many of the students made substantial improvement in their mapping ability with careful teaching over the semester-long course. We do see that experience correlates with better performance. For example, the Bora Peak 3 map and the Kumamoto map were done by the mappers with the most experience and generally performed better than most of the other maps. But we conclude that these experienced mappers still missed ruptures, and therefore we can't just ask experienced mappers to produce these pre-rupture maps and expect that they'll anticipate all of the subsequent ruptures. Here is a table that looks at the rupture to fault separation distance. First looking at predicted ruptures, then sorted by rupture ranking, then the confidence of the fault, and then we have several statistics, all in meters, that are looking at the mean, the standard deviation, and several percentiles. And I'll just summarize several points here. The first is that the separation distance between the ruptures and faults generally increases with decreasing confidence. To our first order, the results that we see here are consistent with Peterson et al. 2011. Likely, this is partially reflects the fact that our prediction criteria followed their numbers. But we also find that this is interesting given the fact that we used students to complete most of the maps and that we looked at a varied location, climate, as well as fault type. We find finally there's a 16-meter separation distance between strong and distinct faults here, and that is approximately consistent with the 50-foot minimum setback distance for California's Alcoz-Priolo Earthquake Act that is implemented after a site-specific study. So the last part of this presentation, I'll be looking at how we can use these statistics to derive fault uncertainty zones. So here's the only equation in my presentation, and that's that this uncertainty zone width is equal to plus or minus 2 sigma. So I'll describe this briefly. So the sigma is the two-sided standard deviation, and the two-sided aspect accounts for ruptures occurring on both sides of a fault. And assuming a normal distribution, there's then approximately a 95% chance that a predicted rupture will be within this uncertainty zone. And so here in this figure, you can see here the fault is shown in blue, and this uncertainty zone here, the 2 sigma, is shown in black, and this would have a 95% chance of containing a predicted rupture. So I then looked at applying these predicted, or these uncertainty zones, to several of the pre-rupture maps. This is looking at Bora Peak in an area where there is a fairly prominent pre-rupture fault scarp. And on the right, you can see the mapped pre-rupture faults in red and purple. And then the principal rupture is shown in blue, and the uncertainty zone for principal and predicted ruptures is shown here in green. And that does contain the majority of the primary ruptures, as we would expect from this analysis. These distributed ruptures are outside of these uncertainty zone. Again, that's not surprising, as these ruptures didn't have any evidence in the pre-rupture evidence in the topography, and they're also distributed ruptures. Here's an example of these uncertainty zones for the Kumamoto earthquake. And here, the pre-rupture map is along this hill slope here, and then crosses the agricultural landscapes. And the fault uncertainty zones do span the rupture that occurred along the hill front. Unfortunately, the fault uncertainty zones do not contain these ruptures that cross the agricultural landscapes, and these ruptures did have no pre-rupture evidence, at least in the topographic hillshades, and so this is expected that these ruptures are outside of that fault uncertainty zone. So here are the conclusions for this part of the presentation. In this study, we assessed the accuracy of our pre-rupture fault maps completed in a desktop-based study using remote sensing data. We found that 12 to 68% of the co-seismic ruptures were predicted by our pre-rupture mapping. Mapping future ruptures is an underappreciated challenge of fault displacement hazard, even for experts. We found that the predicted ruptures were separated on average by a few tens of meters from well-mapped faults, and 100 to 200 meters for uncertain faults. And our results inform the development of fault uncertainty zones for displacement hazard applications, as well as the accuracy of regional mapping that supports later work on site evaluation, regulatory zoning, and paleoseismic trenching. So that's the end of our presentation, and I'd like to thank everyone here for listening to our presentation today. And I'd like to acknowledge the funding that we've received for this work from Pacific Gas and Electric. And we'd be happy to take any questions.
Thank you.
Thank you very much for the really nice both presentation. And yeah, there is any question from people in the room? Okay, Stefan.
If I remember well, you analyzed an earthquake in China, in Tibet, something like this, no? I don't remember no.
We didn't analyze actually any earthquakes in China because we attempted to get pre-rupture data, but we're not able to get any data that warranted this study.
Okay, because at the beginning, one of the first slides was with a 30 meters resolution DEM in, I don't remember, in Asia, but I don't remember exactly where.
Yes, we did look at Nura, and
yeah.
We actually, didn't do that full analysis on the Nura earthquake.
Okay. Maybe I have another question. At the end of your presentation, Chelsea, you have shown the level of prediction, more or less, if I understood well, and you got your prediction is based on a symmetric hypothesis around the fault. So did you try to do something asymmetrical for normal faults or reverse fault, which are usually, yeah, I know hanging wall is more ruptured usually.
Yeah, so we didn't look at any sides of where the ruptures occurred relative to the pre-rupture mapped. Our statistics just represent that offset, that distance between the mapped fault and the rupture, whatever side they occurred on. And we did do beyond just the normal statistics. So we did 1 percentile statistics and log statistics to acknowledge that these distances may not all follow normal distributions.
Thank you.
I have a question. Thank you. Very nice talks. I have found the talks really inspiring. Also for teaching procedures to systematically approach the problem. Really, I find this really inspiring from this point of view. Also for the upcoming publication on this. I suppose you will publish also the procedure, the nomenclature, and the ranking strategy, etc. So I have a couple of questions, one for Rachel and one for Chelsea. First, for Rachel, you ranked the mapped fault, not the ruptures, the mapped fault as primary and secondary. Is good because in general also ruptures are ranked in the same way. So maybe you explained, but I missed something. Which criteria did you use for separating a primary from a secondary feature in the field? Is it the length? Because if I remember, for example, for Kumamoto, there is a secondary which is quite long. So very basic question, which kind of evidence you used for distinguish between the two? And the second question is for Chelsea. Is okay? You have shown us 2 examples with 2 different resolution topography for pre-rupture mapping. One is from aerial photos, I suppose low quality, and another one is from LiDAR. So did you find different zones from the two databases, showing that the resolution can be important in defining uncertainties?
You want to answer first, Rachel, and then I'll answer the other question.
Sure. During the course, we did give some base guidelines to try and teach students to separate primary from secondary in a very general sense, or just along guidelines, like if it was very continuous and along strike like lengthwise, or if it was more discontinuous, parallel to one another, sub-parallel, or approximately like perpendicular to the main fault trace. But we did emphasize that depending on the faulting environment, the level of data, and the type of fault, that we can't provide really hard and fast rules about it. And we didn't emphasize too greatly on at least the accuracy to novices about the importance or the accuracy of doing primary versus secondary, as much as we emphasized as the accuracy of the fault location itself. But we did provide some like kind of general guidelines to try and help them train their eye to it. And it was up to them to decide whether they wanted to classify it as primary or secondary.
And to answer the second question, looking at data quality, we did find that generally, chronologically, the rupture prediction improved with date of earthquake. And so the later the earthquakes were better predicted generally than the earlier earthquakes, and we attribute that to the improved data quality over time. With that said, though, our maps were completed by different mappers with different experience levels in different climates with different geomorphology, and so there were many parameters that were varying at the same time. So generally, we conclude that better data does improve that pre-rupture mapping. But again, there are many other parameters in the landscape that can impact the mapping quality as well.
Thank you.
And I guess I'll tag on it because you had mentioned it a little bit earlier. In the paper that we're finishing up, we will publish the shape files, like the JR shapefile and the fault confidence ranking shapefile, to be able to be used by whoever would like to. Along with a full documentation of that mapping approach with step-by-step instructions for using it.
Okay, is there any other question? Okay, if not, I just want to announce that if you are looking for congresses in 2024, which will be a busy year, but you can have a look at the ESC, European Seismological Commission, which will be in Corfu, Greece in September, and we just proposed a session about fault displacement and surface rupturing earthquakes. So as soon as we will have official communication, we will share, but Corfu in September can be a good option, I would say. And well, about the next talk, we probably organize for January a following talk, and the date is not decided yet, but probably Stefan will be, together with Sebastien, will be the speakers, and again, as soon as we have a date and the timing, we will share the information.
Probably, yes. Not sure.
Yeah, but we will try. So thanks again to Rachel and Chelsea. Very, very nice presentations, and we will think about that and read your papers and improve our teaching, hopefully.
Thank you for inviting us to speak here today.
Thank you.
Yeah, thank you.
Thank you. Bye.
Bye-bye.
Bye.
Thank you. Bye.